back, everybody, to another edition of No Hair, No Problem. Rosenwald here, getting ready to talk about Unit 8, Chapter 8, Section 3, which deals with geometric sequences and series. In the last section, in 8.2, we talked about arithmetic sequences and series, and we talked about common differences. Well, in this section, we're going to be talking about geometric, which deals with multiplying and dividing by the same values. I'm gonna give you guys fair warning though. My kids are gone right now. They're probably coming home soon, and I would not be shocked if they dropped in on me. So just so you know, there's a possibility that we might have some visitors here, okay? But that said, let's go ahead and get started, okay? So when we look at geometric sequences and series, what we're talking about again is we're talking about the idea that we're multiplying or dividing by the same amount. How does this compare to arithmetic sequences? Well, if we remember with arithmetic, if I had a series such as 8, 13, 18, 23, and 28, what was happening was we were adding the same amount over and over and over and over, or we were subtracting, and we called that value a common difference. Well, as we said with geometric, what we're doing is we're taking a value, we're either multiplying or we're dividing by the same amount over and over and over. So in this example, what I'm doing is I'm taking this 8 and I'm multiplying it by 5, and that's going to give me my next number, which is 40. And then I take that and I multiply that by 5, and I get 200. And I take that and multiply it by 5, I get 1,000, and then 5,000, and so on and so forth. In this example of this geometric series, what you can see happening, I'm going to mention this later here, is that if I continue doing this, this value is going to get large. It's going to grow forever. Because the next value we're going to have is 25,000. The next value after that is going to be 125,000, and so on and so forth. So if at some point I ask you to find the sum of every single one of these numbers, what we're saying is that the sum of all these values is going to end up equaling infinity, or it's not possible to add these up because the values diverge and they just keep getting larger and larger and larger and larger, which compares to another example, which we're going to do later on, okay? So when we're talking about geometric sequences, as we said, that change that's taken place from one value to the next, we call, instead of a common difference, we call it a common ratio, okay? An R value that's taken place. So how do we find this common ratio? Well, it's kind of said right here that what we're doing is we take the second term and we divide it by the first term. And that's going to give us a ratio. We take the third term and divide it by a second, and that should give us a ratio. We take the fourth term and divide it by the third, and that should give us a ratio. As long as we have the exact same ratio going on, as long as we have an R here and we have the exact same R right here, then this is a geometric sequence. But if by chance we have one R in the first instance, and then we have a different R in the next, and then another R, this is not a geometric series, this is some other kind of series, okay? So let's look at some examples of geometric sequences. So the sequence whose nth term is 2 to the n is geometric. Why? Well, here's why. If I go ahead and I put in 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power, what's happening is here we can see that there's a change that's taking place that is multiplying by 2. Well, how do I know that? Because what happens is when I take the terms and I divide them, 4 divided by 2 is going to equal 2. And if I continue this pattern here, we can see that right here, I go and do 8 divided by 4, that equals 2. 16 divided by 8 equals 2. So the common ratio that's taking place here is a 2. Now, it says that we're actually beginning with n is equal to 1. That's important to understand, when n is equal to 1 or n equals 0, you'll see some problems where they mix it up a little bit, okay? But if we start with 1, we have 2 to the first power, 2 to the second, 2 to the third, 2 to the fourth, and so on and so forth until we get 2 to the n power. Okay? Geometric. It's multiplying by 2. Here's another one. The sequence whose nth term is 4 times 3 to the n power is geometric. Why? Well, the common ratio between these terms is 3. How do we find that? If I go ahead and put in 4 times 3 to the first power, this is going to generate 4 times 3, which is just 12. So that's when our first term here is going to be 12. If I do the same thing and I go 4 times 3 to the second power, this is going to be 3 times 3, which is 9. 9 times 4 is 36. So this is n is equal to 2. And I can continue this, n is equal to 3, n is equal to 4, and then this goes on forever. What's the common ratio? We're going to take our 36 and we're going to divide it by 12. And what we end up seeing is that we get a common ratio of 3, which is what's stated in this problem, okay? And if I continue this trend looking at it, 108 divided by 36, this is going to equal 3. 324 divided by 108 is going to equal 3. So the common ratio in this problem is 3. Okay. All right, let's go on to the next one here. So examples of geometric sequences where there's like an nth term that's actually a fraction instead. Instead of it getting bigger, it's going to end up getting smaller. Notice in these two, we go 2, 4, 8, 16, it's getting bigger. And when we look at letter B, you notice it's also getting bigger. It's going 12, 36, 108, 324, and so on. It's getting bigger. Why is that? Well, that's because my common ratio that's taking place here is a value that's greater than 1. So it's going to keep growing exponentially bigger. What about when I have a value where it's less than 1? What happens as it becomes less than 1, or as it's less than 1 for the common ratio? Well, here's what this looks like. If I start with negative 1/3, we're going to have just a negative 1/3. That's our starting value. But if I put in a negative 1/3 to the second power, that's where we end up getting that positive 1/9. Then I put in negative 1/3 to the third power, and we're going to get negative 1/27. And then we go negative 1/3 to the fourth power, and we're going to end up getting a positive 1/81. And what we should notice here, this is what's important, is that as we look at these values, as we move down this pipeline here, our values are not actually getting bigger. They're actually getting smaller. Not only are they getting infinitely smaller, they're getting smaller towards a certain value, 0. Because if I end up making this extremely large for the denominator, we would have 1 over big number. And the bigger the number is, the smaller this value becomes, being 0.000000000, so on and so forth. And that gets really close to 0. So there's like a value that we're converging on as n approaches infinity. So this is going to go into something that we're going to deal with here in a minute, okay? So when we look at the common ratio here, it's 1/3. Now, if you can't recognize it right away, that what's happening is I am multiplying by negative 1/3, and then I multiply by negative 1/3. If we can't see that right away, which is okay, that's going to happen, all you have to do is take the second term and divide it by the first term. So this is a complex fraction, which a lot of people struggle with complex fractions, okay? So if we have this 1/9 and we're dividing it by negative 1/3, how do I actually go about simplifying that? There's a shortcut that we talked about before, which is to go ahead and take all of this and multiply it by the least common denominator. Well, if I have a denominator of 9 and the denominator of 3, the least common denominator of these is a 9. So if I multiply the top by 9, multiply the bottom by 9, what we're going to end up with on the top is just a 1, because these 9s will cancel. And on the bottom here, we end up with a negative 3. And there's my common ratio, that negative 3, or negative 1/3. Okay? And so we have a common ratio of negative 1/3. We can see that this is happening throughout the problem. So that's going to, this is an example of a geometric series with a ratio of negative 1/3. So what if I asked you to find a rule that's actually taken place here? And why is there a rule? Well, the formula is actually derived. This is our formula right here for the rule for a geometric series. Same as this rule up here. And it comes from the fact that when we look at what's happening with it within a series, our first term is just our first term, right? The next term in the series is whatever the first term is times the common ratio, okay? The next term in my series is whatever the first term is times the common ratio again. So it's A1 times R, and then the common ratio is going to be applied again, so that's going to be R times R. So remember an example is like, let's say the common ratio is 2. That would be 3 times 2, which would be 6. And then times 2, which would be 12. And then times 2, which is 24. And then times 2, which is 48. And what's happening here is we have the original value, which is a 3. And then I multiply it by 2. And then I multiply it by 2. Then I multiply it by 2. Then I multiply by 2. And what's happening is we're doing this over and over and over and over. That's where my common ratio takes on that exponent that we're talking about. This right here would be 3 times 2 to the second. Okay? This times here would be 3 times 2 to the third. This right here would be 3 times 2 to the fourth. And if I continue doing this pattern and I do this indefinitely, you'll always notice that when I look at this, when we look at this, there are 5 terms that are going on here. You see that there's 5 terms, right? There's 5 terms that are here. But the number of 2's that are involved is 1 less than how many n's there are. So there's 5 terms, but we only have 4, and that means that we have 1 less r in the overall problem. And so this is where our formula is actually derived from. So how do we use this to actually generate some formulas for us? And, oh, there's another formula here, sorry. The other formula here is we're talking about the sum, okay? This goes into when we have this formula, and if I say that we're going to go on to n number of terms, we're going to remember, just take, and when we're doing the sum, this is a partial finite sum, we're adding together n number of terms. So this is the formula that we use when we're adding together n number of terms. And this is the wonkiest formula, I think, of all of the ones that we use in this unit, or at least in this first couple of sections, okay? We'll come back to this in a second. Let's practice using these formulas, okay? I want to talk about this one because I missed an example of it here. If I said, let's write the rule for this, and we have something like, I don't know, let's go with like 100, and then I divide this by 10, we end up with a 10, and then I divide this by 10, we end up with a 1, and then I divide this by 10, we end up with 1/10, and I divide this by 10, we have 1/100th, and I do this forever, and I say try to come up with a rule for this. The rule is pretty straightforward. It's whatever your first term is, so 100. My common ratio for this is when I take and I do 10 divided by 100. So 10 divided by 100 equals 1/10. So that's my common ratio is 1/10. And then my n minus 1. So this would be the formula that can help me find any term in this series. If I want to find the 5th term, 14th term, I just plugged in that value for n. Okay? But let's talk about the sum part. This is where people get a little wonky with it. All right? So what we say when we're looking at this is that we are talking about a sum where we're starting with the n is equal to 1 and we're going up to n is equal to 12. And we say, well, how many terms are we dealing with here? And you remember, the rule I say is you look at these 2 here and we say whatever this is, 12 minus 1, which is 11, and then whatever that difference is, you add 1. Trust me, I'm trying to help you to, alleviate any problems there might be. Because sometimes there's a 0. I went through to numerous students throughout this last week here, and we were working on this. And I asked how many terms are they, and people looked at these 2 and said there's 11 because they said 12 minus 1, there's 11. I said, remember, there's 1 more than what you actually see. Because remember, if we look at the sum, we say from 1 to just 5. Everybody looks at it and goes, okay, there's only 4. And there's not. There's 1, 2, 3, 4, 5. There's actually 5 in between there. So there's 1 more than the difference that's going on there. So if we're going to go ahead and write out the partial sum here, we're going to have a long list that we would have to make. If there's 12, that means we're going to have to write out all of the terms here. So the first one, when we look at this, would be 4 times 0.3 to the first power. Okay. The second would be 4 times 0.3 to the second power. The next one would be 4 times 0.3 to the third power, and you keep doing this on and on and on until you get to the 12th power here. Now that's a lot of work to try to do. This is why we have a formula that makes it a little bit easier. We have to first figure out what the common ratio is for these. And if you remember your formula, A1 times r raised to the n minus 1, the r right here is equal to 0.3. Okay? And so when we look at this information right here, we've got that the first term in the series is 4 times 0.3. You can see it right here. This is our first term. And then my common ratio, we just said is 0.3, and we're finding, as we said, 12 terms. So let's just use our formula, okay? Our formula says it's whatever the first term is times 1 minus our ratio raised to the n power, which is going to be 12 in this case, divided by 1 minus r. So if we put in those values here, this is what our formula looks like. 4 times 0.3, which you can get that. It's just 1.2. 1 minus 0.3 to the 12th power divided by 1 minus 0.3. Throw this into your calculator. Make sure we use fractions, use decimals. And what's going to happen is we simplify this. We get that the sum of the first 12 terms would be approximately 1.71. Okay? All right, so let's look at when we talk about an infinite versus a finite geometric series. So in this example, what we're talking about here is that this is saying when the r is less than 1, we're actually converging on a certain value. Versus when r is greater than 1, it's not possible to actually find the sum. We can't find the sum when r is greater than, because remember that it's diverging, it's going away from a certain value, and it's just getting infinitely larger, so I can't add that together. But when the r is less than 1, it converges. And we get this formula. And as it says right here, you can see it says, it can be shown that Rn becomes arbitrarily close to 0 as n increases without a bound. Now, what does that mean? So this goes on to what we had talked about here, that as if we have a ratio right here, let's say it's equal to just something simple like 1/2. And I raise this to an n power. And that n gets really large. So again, let's say that I have, I don't know, 1/2 to the 52nd power. Okay, big number, really big. What that means is that we have 1/2 times 1/2 times 1/2, and we're going to do this literally 52 times. Well, that means we have 1/2 to the 52nd power, which is a really large number. So 1 divided by a big number means that this overall value, as n becomes infinitely larger, is going to approach 0. Okay, so as n gets really large and we have a ratio that's smaller than 1, it means that that overall value is going to get closer and closer and closer to 0. So what that means is that I can just go ahead and ignore this part of my equation. And now if we take this a1 and we distribute to the top, so we have a1 times 1, we get a brand new formula which says, as my infinite series is taking place, as this goes on forever, okay, my first term divided by 1 minus r is what is the sum of an geometric series. Okay, so let's put this one in action. So we have two different problems we're going to work on here. The first one being, we're going to say, what is the sum of infinite number of terms starting with n equals 0 of this series? Okay. The second one is going to be what happens when I take 3 and I add 0.3 and I add 0.003 and I add 0.0003 and so on and so forth, and I do this indefinitely. All right, that's what these ellipsis points here at the end mean with no value over on the side. It means it's running forever towards infinity. So when I go ahead and I put in this first one here, 4 times 0.06 to the n power, here's what this looks like. We have 4 times, right here, we have 4 times 0.6 to the 0 power, because we're going to start from 0. Well, anything to the 0 power is equal to 1, so 4 times 1 is just equal to 4. So that's where we get this first value here, when n is equal to 0. Okay. When we have n is equal to 1, we're going to have 4 times 0.6 to the first power, so it's still just 4 times 0.6. When n is equal to 2, we have 4 times 0.06 to the second, and we can do this again indefinitely. And so what ends up happening here is, let's use this formula because we know it's an infinite series because we have this infinite sign going on here. Plug in the values. We have 4 divided by 1 minus 0.6. Super easy formula. You just got to put those values in, and we can find that the sum of this actually equals to 0. And what does that mean? Well, if we looked at this first part, we have a 4. 4 times 0.6 means that we have 2.4. And then so on and so forth. If I took all of these values and I did this forever, it's going to equal 10. Okay? Let's do that for another one here. If I have 3 and I add 0.3 and I add 0.03 and then I add 0.0003, what's going to happen is we look at this series. We have 3 times. And we can look at the common ratio here. Okay, if I do 0.3 divided by 3 to get that common ratio here, what's happening is we're going to do this and we're going to have 0.1 is the difference when I do the division here. And that's where we get the formula an equals a1 times r raised to the n minus 1. And we can see that my first term is 3, my common ratio is 0.1, and it's raised to n minus 1. And so this is where we're getting these values here of this 0.1, 0.1 squared, 0.1 to the third, and so on and so forth. So that's used in our formula. Okay. So when we look at this, we know our first term is 3. We have 1 minus r. So that's just using this formula, A1 divided by 1 minus R. We get 10/3, which is approximately equal to 3.3 repeating. And that should make sense because that's what we have when we keep adding all of these 3's together. Okay? All right, let's do one more example here, excuse me. And this is one that relates to what's called annuities. Annuities are great. You should all set up an annuity. If you start working and you want to save up money and you want to possibly like accrue some free money because of interest and you want to use a vacation account, you should do this. Like I have right now set up an account where every single paycheck, I don't even think about this money. It's not part of my daily life. We just ignore it. It's not there. It automatically goes into a separate account that's with my credit union. And that money at the end of every school year, we know is there because we use it solely for vacations. So it's an annuity because every paycheck we put a certain amount in, every paycheck is earning some interest, and we want to know what's the balance at the end of all 24 of my payments for the school year. Okay, 2 payments per month. So what does this look like? Well, I'm going to take, in this case, $50, and I'm going to put it on the first day of each month. Month number 1, I put in $50. I'm going to earn 3% interest on that. And that's going to be compounded monthly. At the end of 2 years, 24 months has passed. Okay, this is important. This is on our test that we took too, that 2 years means that 24 months has passed. So here's the formula we know related to compound interest. We know that we take a starting amount, which is our P. We put it in at a certain rate. N is the number of times, which in this case, if it's monthly, we know that N is going to equal to 12, right? And we're going to do this for 2 years. Now, we're not doing this one time putting in and just letting it sit there. We're going to keep adding to this. So here's what this looks like in the grand picture. To find the account balance after 24 months, we have to consider each of the 24 deposits all separately. Now, there's a bigger formula we can use for this in the financial world, but we're just breaking this down to what we're used to right now. So here's what this looks like. I'm going to take $50, and I'm going to let the $50 ride. It's going to earn interest monthly, so that's that 12 that's going on right there. And it's going to do 12 times, it's going to do that, for 24 months. Okay? And so just for that $50 alone, just for that 50 alone, we're going to earn 50 times 1.0025 to the 24th power. Now that's going to sit there for 24 months. The second deposit, though, is not going to be there for 24 months. It's only going to be there for 23 months. And that amount, is going to look like this. 50 times 0.03 to the 12th for the 23. Notice the difference here. The first deposit's going to be there for the full 24. The second deposit's only going to be in there for 23. So let's continue this. The next deposit is not going to be there. So this is what the 23 would look like. If I keep doing this, the next deposit would only be in there for 22. The next deposit would only be in there for 21. The next deposit would only be in there for 20 months because I'm doing it after so many months has already passed. The last deposit is only going to sit in there for 1 month. Okay? And so this is why we have just a 1 for the last one. Now, what we're supposed to do is take this and add them all together. The total amount that's in there is the $50 that's in there for 24 months. The next 50 that's in there for only 23. The next 50 that's in there for 22. The next 50 that's in there for 21, and so on and so forth, right? And so using our formula, we know that my first amount that was put in was 50 times 1.0025. That came from all the way back up here, which is, where'd it go? Right here. Okay. And that's my initial deposit is just me just putting the money in. The rate on that is 1.0025, and we know that N is going to be for 24. So let's go ahead and plug in our formulas. It's the sum of a finite series. This ends after 24, not indefinitely. So my first term, when we look at this, is that 50 times 1.0025. Our money went in for 24 separate months, and the ratio on this was 1.0025. Throw this in our calculator. At the end of the 24 months, we have $1,238.23. Now let's talk about the power of interest here and how cool this is, okay? If we were to look at this, we did $50 and we only did this for 24 times. Right? We put in $50 24 times. That means that there's a 0, a 2, this is 10, this is 12. We put in $1,200, okay? But at the end of the 24 months, well, we only put in $1,200, we have $1,238.23. We made $38 of free money. And this is where, when you go to put your money in, you try to find banks that are going to have a high interest rate so that you can actually accrue more free money over time. And just remember, this keeps spiraling, man. The more you put in, the more interest you earn. The more you put in, the more interest you earn. So start early. That's how you make money in the world. Okay? This pretty much concludes everything in this section. All the problems you're going to see are some variations of these, but remember, just use the formula, plug in what you know, solve for what you don't. And I think you guys should have no problem doing this. I'm going to tell you, though, because there's a lot of fractions in this, a lot of decimals, this does get a little bit more challenging, okay? But you take care, stay safe, stay responsible, like and subscribe to my channel, and we will see you next time. Take care.